coming after me to say something about myself. My name is Vic Maller. I hold the ICL chair of computing at Loughborough University. I was formerly with the ICL Research Centre at Stevenage for some 22 years. Before that, I worked for the Royal Navy, playing with radio controlled fireworks. Between becoming an academic and leading at ICL, I was technical director of high information technology, and then set up my consultancy business. So I've done quite a number of odd things from time to time, and I'm now sort of quasi-academic, not quite in, not quite out. Having said that, let's get on to the business of CAFS. I left this slide up here to start with. It was the copy of the award that was given by Lord Kearton some years ago, in 1983 to be precise. ICL was given this award of product of the decade. But what else has CAFS done? Written around the press, the great ICL innovation. It was first delivered in 1979. Product of the decade, 73 to 83, as mentioned. Green's water technological achievement in 1995. Thousands have been sold in ICL mainframes. And it's now been reduced in size, but not in functionality or power. It was appearing on mid-range Unix machines and the larger PCs. It was released on those some 18 months ago. But what is it? And why is it important? Well, the term file store, I think, self-explanatory. It's a device for storing files of information. The content addressing is somewhat more contentious. Content addressing is sometimes called associated with access. And it is, in fact, a storage mechanism in which the data is accessed by using its intrinsic properties rather than by some addressing mechanism, some indexing mechanism as such. And in the minds of users, information is always identified by means, identified by its intrinsic properties. And if one's a layman faced with computers, one says, well, what about it? So don't computers do it anyhow? Can't they understand the intrinsic properties of data and use that to access it? And to which the answer would go, yes, but sort of, but they're not really very good at it. And this was how the analysis of the problem, which led to the origins of CAFS. Let's say a little bit about searching first. What do we mean by it? It's a natural human activity. Faced with the possibility of finding something, we will try and use various methods to restrict the search space, even though it's only storing all the same things at one particular subject on a particular shelf. So we use classification schemes, we physically partition the information, use catalogs, and so on. If we're enthusiastic librarians, we'll use indexes, and perhaps we'll have one-dimensional indexes, the main index, cross-referencing indexes as well. But indexes are always slightly confusing. They've been asked to have it. Many human organizations getting out of date. Constantly have to be rebuilt and recompiled. And the same, sadly, is also true of computers. Moving to how the computers do it, or how conventional machines do it, they use some form of explicit referencing structure, indexes or lists. If all else fails, they will search. Can you all hear me? I prefer to use microphones I can possibly avoid. Now, I said that computers aren't very good at accessing things by what's in them. The only way a conventional machine can do it, in fact, is to search linearly through a particular set of data. Or else use some form of explicit referencing structure, some list or index structure with which to refer to it. And indexes are essentially a means of doing sums. And conventional computers are very good at doing sums. And so calculating an address for various starting points is a perfectly easy thing to do. But it is rather like staggering from signpost to signpost in order to get to where you want to be. If the indexing system fails, one has then to fall back on search. But of course, in many conventional systems analysts, this is the last resort to the incumbent. If you analyze your problem correctly, design your data structures correctly, instruct the appropriate referencing structure, of course, you can always get to what you want reasonably quickly. Anybody with any experience applying in the field knows, of course, that this is complete nonsense. Yes, there are applications which will be partially supported by such mechanisms, but many which will not. And the other problem that comes up, of course, is that systems themselves requirements for systems change and are moving target. And the systems therefore are never stable. The idea that one can actually build some computing system and carve this from some granite, as it were, leave it there for all time is, of course, completely inappropriate. We live in an age when there's continuous requirement for systems to be changed, modified to growth, and suit continuously changing requirements. This plays no carry. If one spends an enormous amount of effort building some large, complex structure, the only means of changing it would be completely population. So we come back to the problem of search. And even those hard-bitten system analysts will actually say, well, perhaps there are occasions when searching large quantities may be justified, but of course, never do it online. Now, if we actually look at data processing through the last 30 years, much of it is concerned with extracting loads of information from files by single or multiple key matching, even as a linear search down a file. This, in fact, is a form of content addressing, although it's not necessarily appreciated that that's what it is. And even fairly early on in computing, electronic computing, die-hard engineers, systems engineers, had to concede that content addressing could have its uses as a simplifying mechanism for access if it could possibly be built. The advantage was recognized in the early 1960s. The technology was not up to it. If we go look at what's happened in the last 30 years, and look at what our users actually want from our computer-based information systems, they want easy access to stored data. Now, of course, they're increasingly working interactively with computers and expect a rapid response to everything they do. They also want an answer from the machine before they've forgotten what the question was. Now, because of the difficulty in the early days of building any form of associatable content addressable store, one had to fall back on indexes. And a whole school of thought grew up that surely indexes augmented by searching perhaps is the right solution about in the two. And the only problem with computer-based indexes is their utility is too often merely taken for granted. Clever indexing may be inefficient, but it will always find what you want. Indexes are in fact extremely primitive projections of files. They do not satisfy the totality of useful search requirements. They can also be very complicated, computationally intensive to build, and often can only do certain limited tasks. Anyone has, in say, some text retrieval systems, the absurd situation has occurred that the embedded files that are associated with them, that the indexes have actually occupied something like 4 times the storage space the data itself occupies, which is a grotesquely absurd situation. They do, however, work well, as I mentioned, in well-characterized applications. But there is this problem of unpredictability. And the classic one was known in the trade as ad hoc query. There's also the problem that human genius brings precision, which is recognized as fuzzy matching. Now, for instance, an example of what that means. Some of you cast your mind back to the days of the Carter administration in the US. Carter had a national security advisor, a Polish American, whose name was Brzezinski. Most people couldn't pronounce it, let alone spell it. But they knew, unless they were Poles, they knew it began with a B. It perhaps had an R in the second letter. It had a Z somewhere in it, and it ended in SKI. Now, I defy any indexing system to find that name in the list of name addresses. It can be very simply done by a search engine that employs finite mistake techniques. And so we see requirements there for fuzzy matching which can't be easily met without some form of linear search, perhaps augmented by hardware, or certainly requiring some very sophisticated software. So the answer is, then, we can't use indexes for everything. We have to use search after all. Well, search can take a long time. Of course, I might say over the last few years, well, sure, we just throw a computer fire, it's now cheap, get more bangs for the buck than we had before. The question then comes up, of course, what sort of computer power? Because although computers are more powerful and very cheap, what we have done over 30, 40 years is really to replicate different implementation technologies the very primitive very basic von-Neumann computing machine. And what we're talking about here in searching for data is the need for efficient pattern matching. Now one can argue that the very simple computational model of a Neumann machine is very pure. It's a universal capability. It's a universal machine in the Turing sense. But whilst it may be good science, it may also be bad engineering to solve certain practical problems. A conventional von Neumann machine is jolly good at doing sums, but not very good at doing pattern matching. It can be programmed to do it. It's a universal machine. Many people try to write pattern matching programs, knows full well that the number of instructions involved can be horrendous. And it was with that appreciation that we set out to build a special purpose search engine using parallel processing techniques. And that's what gave birth to ICL CAFS. That, right, is just the technical impressions that existed over the last few years, provided part of the rationale for it. What I now want to do is something about how it actually originated. Because the story isn't just one of technology, it's one of people, it's one of organizations, and that, in many ways, is the most interesting part about it. And as an introduction to this, I think I must go back and say a few words about the origins of computing as we know it. If we think of something, it comes in two streams. There is scientific computing, doing sums, which down the centuries has been done by human computers. And I'm old enough to remember that when I first started working for my living, we did indeed have the Alpha Research Establishment where I worked, a department with lathes who used electric Monroe machines, were called computers. They did our numerical computation for us. We had one digital computer in the atmosphere in those days, Pegasus Eddington. So heavy reliance was placed on these human computers. And I suppose I wrote my first program by producing a sequence of instructions in natural language, of course, upon which these girls were able to work. Moving from there to the electronic computer was really a very frustrating experience. These girls have intelligence, they learn about the application, and they can fill in the missing parts of the program for you. The computer, well, need I say more? Now, the abacus, of course, been out a long time. We've had Pascal, adding machines, Leibniz, step vectors, Babbage conventions. But the real key point was World War II, was the development of reasonably reliable electronics and the development of cost techniques. And of course, there were two schools of development. The Americans who were trying to build calculating machines to solve basic ballistics problems, and the British beavering away in the English country house, of course, reading German telegrams. But the results of this technology manifested themselves after the war was over. A universal computing engine could be built and was built. By the early 50s, they were being used for scientific and engineering calculations, and the first commercially built machines were becoming available. The scale of applicability was mostly underestimated in those days. Nobody dreamt of the number of machines now, and then nobody did then the number of machines that we now have. And we now, of course, have, including the scientific computing, everything from a calculator, programming, with the power of the Pegasus machine that I first used 30 years ago, to a crane. Well, these machines are essentially all tailored to doing engineering and scientific computation. And the whole industry supporting that took place quite independently of a quite different industry, which was concerned with data processing. Data processing, that task of maintaining ledgers and files of information, is the lifeblood of commerce. And of course, it goes back a very long way. Archaeologists, when they dig up some ancient site, they find lots of clay tablets covered with early writing, always hope to find some wonderful works of literature written by the people of that period. And when they finally decipher these messages, of course, they are always discussed and find they're really concerned with invoices, bills, and ledgers, and so the sale of sheep and goats. And one such database many years ago was Ebla, which was excavated. And here, in an underground cavern, they found rows and rows of neatly stacked clay tablets. I think one might call it the world's first database. They were all neatly classified there. They were files of information concerning purely business operations. That leads us through into the next century. and data processing of the commercial kind was kick-started by the National Cash Register Company, the tabulating cash register. That in turn led to Hollerith and the punch card era. And for some half a century or more, to electromechanical machines, widely used in commerce by all the major industrial companies in the world. And these systems, moreover, operated with very sophisticated electromechanical machines. They weren't computers, but they could do very complicated tabulations, additions, and even associative matching. During the Second World War, the US Armed Forces had their entire personnel on one very large punch card file, some 12 billion punch cards. And they could pass this file to a bank of Hollerith card sorters in something like 4 hours. They could patch, they could bundle programs on the patch boards of these things to search and say all those Americans of genetic extraction, which could then be sent off by the Japanese. The important thing was that they were doing an associative or a content addressing search. After the war, we had this interesting scene at Lyons, where they actually built a digital computer to apply to clerical automation, which was an astonishing piece of inspiration on the part of the people there. And even after Lyons had started their work, what became known as the Leo machine, Thomas J. Watson at IBM made what became one of those famous last words in the history of computing, when he declared that IBM could see no future for the electronic digital computer in commercial data processing. And judging by what's happened over the last 2 weeks, it seems that IBM has not lost the gift of getting their strategy spectacularly wrong. We now come to a period around 1960s, early 60s, and the CAFS pop. And thinking about what actually happened and evolved, I'm reminded of a statement made by the American philosopher Santayana earlier this century, when he said that mankind will never reach the stars unless some man dreams that they might, some man shows that it can be done, and some man wills that it must be done. And this is very much the case with CAFS, coming down to Earth. Of course, I think that in terms of space travel, everyone can argue that names like Tsiolkovsky and Oberth, those who did it might be done. Goddard and von Braun showed that perhaps it could be done. And John F. Kennedy, of course, willed that it must be done. If we take CAFS, we have 3 names there. The first of which is Gordon Scarrett, who in 1962 dreamt that it might be done. I'm very glad to see Gordon in the audience here this evening. Late Roy Mitchell, in 1970, showed that it could be done. And Rob Wilmot, new managing director of ICL, 1982, willed that it must be done. And these 3 people, more than any others, that made CAFS a success. I'd like to go through the history of that from Gordon Scarrett's dreams. At the time, Gordon was chief engineer of Ferrantis, working on the Orion computer. And the Orion computer was getting to grips with the problems of the early, we now call operating system. And appropriate for a machine called Orion, of course, the system was called Nebula. And Nebula was having problems with the file store. And the Nebula file store was controlled by a magnetic drum. And the way the software engineers put this together, of course, was they were using a list structure. They could block to block and try and find the information they wanted. Of course, if you do this on a drum, one accesses one record in one block, fills block, does some calculations, works out where the next block is, back to the drum, dishes out the next block, and so on. And eventually, after several accesses, you rattle down the information you actually want. They told all this, it's very inefficient. And Gordon said, well, what you need is this. Here you have this drum course, all these tracks spinning around under magnetic heads. If you're a physicist, you would say that the data is being continuously read on all the tracks. There are currents appearing in the coils on these heads. Nobody's taking notice of them. It's just merely an example of your efficiency. If you put some electronics, it will then do a match test against the electronic off the drum. Sure, you could find that block in the record in one pass. Get away. Go on, it never work. Well, they were right up to a point. It was only 3 years after the building of the first transistorized electronic computer, and at that time it would probably require a large room full of electronics to make it work. But the idea conceptually was quite deep and quite elegant. And during the 60s, a lot of work went into the whole subject of associative storage. The problem was there wasn't a convenient technology. What had been appreciated was that one had a homogeneous technology, which you now have as semiconductors, in which one could mix logic and storage. One could perhaps take some form of associative memory. And the only one that successfully made at that time used the phenomenon of superconductivity. It was developed by General Electric in the States under a US Navy contract and built at their Sunnydale plant in California. And it did actually do some very clever pattern matching, albeit of fairly limited size, probably about 20,000 characters the maximum could handle. But it was a bit slow. And of course, one of the problems with superconductivity, as you may be aware, materials that lose their electrical resistance, of course, always make electrical engineers very interested. The only slight snag is in order to switch electric current in such a circuit, you have to introduce some resistance into it. Superconductors have the property to change them back into a resistive state. At very low temperatures, the resistance is very small, although the gap ratio between low resistance and some resistance is infinite. There is a problem known very in the schoolboy electronics called L over R, the ratio of inductance to resistance. And sadly, resistance goes down with temperature, but inductance robustly refuses to do so. And the L over R time constant of all superconducting computers is just too long. But it did work. It made it work. So at that time, this takes us to about 1966, 67. The modern disk file was being developed, and head-to-back disks were coming through. And the next person to do it in this deal was Slotnick at the University of Illinois, Urbana, was building a machine called ICL 4. And he spotted the possibility, or reinvented Gordon's idea in 1969, and he had the same problem as managing the ICL 4 file store, and using his head to track this, and putting search logic all over the heads, and picking off information in one location. And in the spring of 1969, he set a research team and worked on this particular problem. And gradually, of course, information was getting around the scene, and one perhaps could do something with rotating magnetic memories. At this stage, dates here. At this stage, the scene shifts as far as ICL is concerned. 6970, and three people, Mitchell, Caloris, and Evans. John Evans was a research student at Imperial College with George Caloris. They were working with Stevenage on John Ire's basic language machine. And Evans was given the task with his PhD to look at some of the problems associated with its file store. And he chewed his pencil as he thought, my goodness, it wouldn't half help me. We could have one of these disks that actually search associatively. George Caloris said, what a good idea. Let's go and talk to the chaps at Stevenage about it and see what they say. And enter Roy Mitchell, who said, yes, Gordon thought this about 7 years ago, but the technology wasn't right. Now we can buy semiconductor, or we'll be able to buy semiconductor storage, albeit on the chips. It's perhaps time we should reconsider the situation and see whether we can actually build a practical device at that time. So Caloris and Evans were asked to go away and think about the functionality of the machine and what's the language environment to drive it. They also sent the spies off to the United States. Being academics, they thought they were going to be getting to various places that ICL staff couldn't. Their cover was quickly blown, unfortunately, but they nevertheless came back and produced a report. It showed quite clearly to the customers they talked to, the users they talked to, that some form of associative research could pay very handsome dividends. In the meantime, Roy Mitchell had been burning midnight oil and chewing his pencil, and had finally produced a logic design of considerable ingenuity, which made the whole thing practical, which actually worked. The department contained ACTP support from DTI at that time, and set to work building the hardware in 1971. And it built about, no more than 6 months, and it worked. And that's very interesting at that time to take the reaction of parts of ICL. ICL was a company, competent in the field, very much committed to an evolutionary product development. There was a large group of people in the company, away from Stevenage, who were the experts on disks. And their view on this CAFS device was, it would never work. When it did, they quickly shut up. They couldn't very well do anything in face of an existence proof. The software people were more circumspect. They said, and if it works, it's irrelevant. Because everything we can do by software. And of course, they're right. They can program their universal machine to do everything the CAFS hardware can do. What they failed to appreciate was the benefits it could accrue through the use of this hardware as, in effect, an accelerator. And the only example at that time of accelerators in computing was the use of a floating point hardware. That was tolerated. Adding real numbers was fixed length word machine is parsing the tedious instructions, build sufficient hardware to do it, and they go and multiply numbers very much more quickly. But to some extent, CAFS had a somewhat analogous device. The idea was to build an engine which could search files. It was a file filter, especially the hardware it could do. It had its own command set that could handle its operations autonomously, or like a floating point unit in a different area. But this concept was faced very differently. People were very reluctant to actually accept it. Nevertheless, what happened? The group at Stevenage carried on. We produced, in 1972, experimental relational database was running on this first CAFS machine, as well as a text retrieval system. In 72, 73, we actually did an experiment which we combined this with speech input and output, linked to a CAFS supported relational database. And would actually make telephone inquiries on your relational database and get an answer, at least in a different way. But I think that was a world first in terms of what it actually offered. It also talked a lot about the inadequacies of speech as a medium of communicating with databases. In 1973, we set out to design what might be called a prototype machine which would actually be used for trials, real trials in the field. Now, Tony, can I just switch the slides at this stage? I'd like to talk a bit about how this beast works. Not in great detail, but just to give you, those who aren't familiar with it, some idea of it.
On the top of the pillow. On the top of the pillow. The rail.
Go. That's fine. I'm being dazzled by these spots.
Yeah. I think you might find a control along the end of the disc.
Ah, this one here. Thank you, Chris.
I don't think that does, actually.
It doesn't?
Black art.
No.
House lights, what happens here?
No.
No.
See you close. Take the box out.
I can play a tune, but house light, no. Magic.
Come on, Tony.
Focus, please. Whoops. That's it. Hold it there. Now I'm going to just consider a very, very simple processing of inquiry. And let's say we have somebody that we want to give name and personnel code for somebody with a job as a salesman, and with age less than 28, and a bonus rate of 750. Next slide, please. What I want to see to illustrate here is the close mapping between the description of a query at a very high level and what actually happens in the hardware. Well, some software interprets this command and generates from it. Can we refocus again? Seems to have got that's it. Hold. Three parts. We bring out a series of selection terms which are attribute value pairs, job, salesman, age 28, bonus 750. There's then some Boolean expression linking them, in which we're looking for equality between the attribute that's value in the first one, the inequality less than on the second one, and the inequality greater than on the third one. You have a retrieval expression which says we'll bring back the name and personnel code. Next slide. Right. Now, in the hardware, there are a series of things that are called key registers or key channels, into which the descriptors and the attribute, or the descriptor of the attribute and the value are loaded. So we have these three things here. We have these conceptually in a retrieval unit, the descriptors of the data we wish to retrieve. Next slide, please. Yeah. That's it. Now, the data from the disk is streamed through this hardware. Now, the data itself, the records on it, contain each attribute item is self-identifying. I really don't know how this is done, but it was an important feature of the way the system worked, that each individual field, data item, could be considered to be a variable length and carry with an identifier saying what it was. And of course, the data you showed here coming from the home disk, because the disks at that time of the first machines were not very fast. In order to get the speed of something interesting, the very first machine we operated about a megabyte a second, and then somewhere in the region of 3 billion characters per second, the second machine. The only way to get that from the disks at that time was to take the data from all read heads simultaneously and multiplex it onto a single highway. But conceptually, we can just consider one single stream. And I think if they're pouring off the disk here around, let's say, 3 billion characters per second. Now, what actually happens? Well, these individual key registers all working in parallel attempt first to match their identifiers against the data of the stream. If the identifiers match, they can match on the value of the term itself. These individual terms can be masked. The result of the comparison is then stored in a latch. When the end of the record comes along, the hardware says, flags an event and says, I've seen the entire record. I have now done all my comparisons and I got the result stored. I've also, in principle, buffered up the information I wish to retrieve in the expectation it might be useful if the record is subsequently declared to be a hit. Next slide, please. Then what happens is that the program insert evaluation units, kicks into action, and this is executed using as operands the values in these key comparator latches. And the example shown, the expression here is true, and therefore the information is worthy of being retrieved, and the information here can be gated out and ultimately returned to the user. Obviously, in actual practice, there's the element of double buffering here, because while this evaluation is going on, the next record is being examined. The objective of the system is to make quite sure we never lost synchronous with the disk. No matter how complicated the inquiry, we could always keep in step with the disk itself. At the time that this machine was built, large-scale buffers that could buffer whole tracks and whole cylinders of data would be impossibly expensive, different now, of course. So at that time, synchronism with the disk was of key importance. Next slide, please. Just to emphasize the parallelism of it, because the actual hardware that we built this which had 16 key registers in it, here they are shown, all working in parallel on the data stream. What is important to note is that the architecture itself needn't have stopped at 16, we could have put many more in. And in fact, we have the original provision to be 28. We didn't put the additional 12 in, we used the space in the back to make it something else. But that was only a quirk of the experimental system. The architecture was designed to be extensible, so in principle you could extend the number of comparison channels, not by an infinitum, but to a very large number if required. Next slide, please. Now about the performance of this thing, because we've talked about it as an accelerator. There's nothing a conventional software system can't do in terms of functionality. But if we start to compare what a conventional processor can do, we get some very interesting results. Now, we defined a term called the mainframe equivalent, measured in million instructions per second. In order to do this, we got one or two of our extremely competent programmers to write in very well formed and very well tuned basic machine code the functional operations that the CAFS hardware produced. So we could run them against a data stream in a dedicated machine and just calculate count the number of instructions that were executed. And from that, of course, we could work out the power required to make a conventional processor running a disk stream at the same speed equivalent to the CAFS hardware. Now, one of the great features of this was the data structure that we took, which was this variable length field, variable length record structure, enabled us to handle with equal facility both fixed format records of COBOL and relational variety, to loosely structured text, and up to what is euphemistically called unstructured text. And it's very interesting to see the sort of powers we're talking about for a data stream running at around 3 megabytes a second. And if we take a number of terms in the selector, we have to operate the assumption here, of course, that all terms have to be compared, so it's a worst case one. Then we see we're talking about somewhere in the region of about 400 million instructions a second equivalent in searching text. And even with fixed format records, we're well up in the tens of bits range. And that is, of course, doing things it's now just about possible using some of the very modern high-speed RISC chips to build a search engine to run at the same speed as this without using the CAFS hardware, the original machine. So the text, on the other hand, it's still beyond the capacity of any cheap system. Thank you, Tony. Thanks, please. This is just numbers of the CAFS Mark II machine. Its peak scan rate of 3.7 million characters a second was character byte specific to a couple of the old 1900 architecture, and therefore worked with 60 characters. Its peak search rate was somewhere just short of 60 million character comparisons per second. And it was used for many internal trials. It was also used for the telephone directory inquiry trial with live data from various parts of the country in 1967. The search rate of telephone directories was equivalent to searching telephone directories rated on 100 pages a second. That was released as a product in 1979. The last machines were drawn from service at the end of last year. The architecture is very similar to the machine that was first live in Steam Village in 1974. Now, what happened in between times inside the company? In 1973-74, the Mark II CAFS, we called it the Steam Village operational, and we were trying to get interest from the product divisions of the company and also from customers. And our biggest success was undoubtedly the marketing people. We were a research centre. They liked bringing customers around to show us how good ICL was. Of course, there was no guarantee what we were doing in the manufacturing product necessarily. But on the other hand, the CAFS system was known to be an impressive demonstrator. A lot of customers being exposed to it and saw it working. One customer was the post office, and then, of course, telephones. And they were encouraged to consider using this, or developing this, for telephone directory inquiries, which at that time, of course, was entirely manual using books. They looked at various microfiche systems, but that state of technology wasn't adequate. And they were looking for a computer-based solution. So one day they brought some very high brass to our lab in Steam Village, the post office, and gave them a demonstration. They'd given us a copy of the Isle of Man telephone directory before they came. They wanted a demonstration of the Isle of Man telephone directory. So we put this up and we showed the various things, and they all set up poker-based editor. And unbeknown to us, one of the gentlemen present owned a holiday home in the Isle of Man. And he said, well, can you find my home? And he said, I'm not going to give you my name, but I will tell you my cottage is called Acacia Cottage. So we typed in Acacia, I'm not quite sure how to spell Acacia. So ACAC was typed in the script of the house name. Button was to be pressed. Within about a second and a half, back came just the man's name and the rest of the man. But what had actually been done, it had been done by a perfectly well-engineered indexing system. It was so choose to do so. But nevertheless, the fact that he'd been able to answer the query with a term that we hadn't had any foreknowledge of, he found it extremely impressive. He'd already been told by computer people, you must have advanced notice what you want, and we'll build a system to suit your requirements. Here was some deal with the organisation that they didn't ask any question like, and then they built up back the answer. The result of this was that the post office didn't go ahead with the telephone directory inquiry trial using CAFS Mark IIs. Sadly, they didn't want to buy the CAFS system. They chose an alternative solution based upon microfiche for other reasons at the time. The CAFS trial was deemed by the post office to be an overwhelming success. The other area of activity, of course, in the company itself. There's always great danger, of course. The Converse children being the worst job. We were doing our best to try and encourage ICL to do some of the technology for real. Now, this stage, another management licensees in the audience here this evening, Hamish Carmichael, who worked for the company's corporate computing group at that time. He became involved, became an enthusiast in CAFS, and was instrumental in getting various trials carried out with the corporate computing services inside the company. And these quickly produced very beneficial results. Various files were mounted and loaded online for the first time. were as we expected, but it had some interesting side effects. Often the quality of the data in these files was very poor. And they had, the people owning the applications spent a lot of time building utility programs to try and clean them up. When they had the thing actually online and scanned the whole thing in a few seconds, they could do all sorts of probing questions to see what had gone wrong and to improve the quality of the data. And here the individuals who owned the application understood what it was about, would actually ask questions, get answers back, follow supplementary questions, and they only realized when they'd seen the answers to the first. It was a true dialogue with the system, which none of them ever had before. And this encourages widespread use, and it also led to a very interesting experiment for those interested in systems analysis. The Corporate Systems Division decided that they were going to do a controlled trial. They were going to, I think it was the audit database, if I remember rightly, up on the CAFS system. And they were going to do it in two ways. One, they were going to set up a team of systems analysts to go away and do an analysis of the problem, look at all the requirements, do all the classic stuff, use the specification, which you then need to present on the CAFS system. Another group set to work independently, they were told, let's go away and let it play with it. Experiment with users and see what you come to. And the result of this was, in a matter of a couple of weeks, the latter group was business, and they had they were ascertaining all the requirements of the system experimentally in conjunction with the end users. At the end of the same period, 3 months, the two groups adopted it to be paired, and it was a very, very interesting comment on the classical method of systems analysis, with all by doing surveys and requirements analysis and so on, in comparison to the technique of building a prototype and digitally trying it out with the users and defining the requirements as you go. It convinced me at that time that the conventional systems methodologies that were being developed, so-called waterfall model, was fatally flawed and eventually would collapse under its own weight. And all the evidence I have seen in the field leads to so. We're now trying to develop system building techniques that do follow a digital approach, and a prototyping approach. And this was one of the first examples I came across in which this technique was tried. And the only software that needed to make this work was a general purpose inquiry system. In fact, what we actually had was a general purpose database system. Because we had the hardware in the 70s, we built a relational database, a population database on the early machines. We tried that on some company applications and came to the conclusion that the population database was interesting, but was far from perfect. It was too naive representation of reality for the practical cases. And we went beyond that to develop a more comprehensive model based on semantic graphs, which actually met that. The population database dropped out in a special case. And this particular system was then used in a trial software environment for the internal use of the companies. It was essentially an inquiry-only system. The database we set up very quickly, and we reckoned that we could take the files from people and load the system probably within 2 or 3 weeks, and we actually ended up operating on it at terminals. And I can't remember all the applications put in it now, but there was certainly everything from personnel, orders, machine population in the field, and all sorts of things went on this system. And this use of the CAFS became widespread, and it became an established part of the corporate computing group's policy to have the CAFS system available. This was extremely important for persuading the company that we had something that was useful. By the end of the 1970s, the CAFS survived. The Mercury Pirate project was terminated, but a decision was taken to release the CAFS Mark II to a limited number of customers. The general inquiry system to go with it. And this was quite successful. Some very interesting applications were built that CAFS machine, which could not be handled by conventional methods. One that comes to mind was the Civil Aviation Authorities near NIST register. And they found when they had this on CAFS, they could do trails of data, grouping together, classifying various categories of incident very much more easily than they could with any software system they had before. And the reason for this was not that the thing was clever with the software, it was because it enabled the users to have to conduct a high-speed dialogue with large amounts of data. It was power. It made it possible. By the end of the 1970s, the company was beginning to realize it was important to take CAFS seriously, and more people were beginning to say, I think our software would benefit being put on CAFS. And so groups were set up to try and draw specification for a real product. had been signed off, CAFS always seemed to fall over the line. And this was the situation, in fact, until ICL had a very bad patch in 1981. There was a major shakeout of the top management. Bob Wilmot came in from Technical Instruments. And he went around the entire company. He was showing the CAFS, his interest in it. We had, because of it, he came back to the data processing field. He somehow brought a fresh mind to it, and he could see the benefits of this thing very quickly indeed. And he, who then, in, I can't exact date, that was 81 or spring of it, winter 81, 82, of course, made a decision that CAFS should be built, ideally on office systems, but if not, then on mainframes. And he authorized its development. And from that came the first full range CAFS product, the CAFS ISP, which was released on VME range machines. Then it was announced in 82, and I think first deliveries took place sometime in 84. This was essentially functionally it was exactly the same as the CAFS Part 2. Much smaller, much cheaper. Of course, we now had disks, single channels were a few megabytes a second, so we had no need to complicate multiplexing. We also had vast improvements in the electronic and the silicon, so we've actually made it very much smaller. And finally, it was a VLSI version. And then followed further enhanced functionality, and that came out towards the end of the 80s. One's now down a large, I think the size of a wardrobe, to a small module, the size of a small number of cards. And I can see a VLSI chipset going to the next stage, and the whole thing then becomes the size of a cigarette pack. Or rather, it becomes the size of the sort of cards that one plugs into workstations. This, I think, is an interesting change in the industry. The whole idea of accelerators and bolt-on features did not fit in well with the culture of evolutionary development on mainframes. We now have an industry where the culture is simply different, where new companies come along, built small systems of data like power, thinking in terms of companies like Sun and similar workstation manufacturers, let alone of course the PC and the Mac field, where of course the whole idea of plugging in additional modules to do various things is perfectly acceptable. And if you look at any magazine advertising components for these machines, you see accelerators for this, accelerators for that, accelerators for the other. Mostly in the field of video and graphics for the workstation market, because here, of course, the computation required to handle holographics in a sensible way was quite simply beyond the power of even the fastest processors that could be built at a reasonable price. And pretty clearly what was required here was to devise special hardware to do some of the graphic manipulation point. And so again, we had the floating point paradigm being pursued, this time with graphic processing. And no company building a graphics workstation would dream of not using very sophisticated chipsets to speed up the processing of the graphical information. Interesting enough, it hasn't happened yet at the back end database end of machines. Now we are seeing small machines. ICL 2 years ago, or 8 months ago or so, released a thing called SCAFS, which is a small to one-card accelerator which goes into the Unix and PC systems, event PC systems, which is getting down to that level of the market that one can buy these devices as a file accelerator to work on these machines. And in fact, what has happened here is that the relational databases that are sold by ICL, Ingress on its mainframes, on its Unix machines, and Infomix on its Unix machines, have all been modified to run the CAFS hardware as an accelerator. And interestingly enough, the Ingress, American company, had to change the source code for this. And things like American, because often the American companies always European, aren't they? But the problem, of course, with using CAFS is that it needs to be, the software needs to understand it at a very low level, which is to explain properly. And one of the early problems we had, when it's attached retrospectively to existing software packages, was it didn't provide anything like the performance gain which should have achieved. What I understand Ingress has now done is they've modified their master source, the Ingress relational database system, such that when it's loaded to a new machine, it always tests whether a CAFS module is present, and if so, it will do certain things, if not, do something else. So if one is running Ingress on brand X machines, the CAFS software is there to drive it. It's sad to have a CAFS module on the brand X machine. What about CAFS in competition? I showed some of the processing powers, and of course I could go on showing slides as the cows come home about some of the things it does, but I do love things like this. where we see standard IBM software package running on a fairly large machine, and compare what goes on down there, what goes on up there. USA law. The one that I particularly like is a quite different field, because most of the CAFS applications have been the field of commercial data processing. There have been some scientific applications as well. And this one was nice. It's Queen Mary College. They had a 2988, which they with CAFS ISP modules on it. And they were in the game of processing data from the IRS satellite. This was around 1985-86. This was an American red astronomical satellite. And they were given access to the data, the point source catalog, see all the sources they had in the sky, some 400 million sources, and 600 megabytes of data. And to process and classify this requires some quite clever software. And the US had access to a cray, and it took 20 minutes of dedicated time on the cray to search the entire file, to exercise what to test a hypothesis on the file. It took at least 20 minutes in batch mode. Here you see a couple of CAFS ISP channels, 1998, and could obtain answers directly in less than 2 minutes. And for them, the great joy was that they beat the Americans in interpreting their own data in many cases, established their own inventions in the world as a result. And it's entirely the result of not just the speed. The speed was reduced to a point at which they could do it interactively. They could test a hypothesis, it didn't work. Twice it just change it slightly, press the button, run it again. These guys, of course, were separated from their machine by the equivalent of the wire basket button. They set their program down. I know they do it to the terminal, but it went into a queue. They go away and have lunch, and it's lucky they get the answer back. If you're doing that, the process of iteration and refinement is made very much slower. It's also severely prejudiced because the mental processing of the individual loses the context, he has to rethink what he's doing, and the whole process becomes much, much slower. It was the 2 minutes on a couple of CAFS channels. It's not whatsoever it's cost anything. Maybe low thousands of pounds at that time in comparison with a very large cray machine. What about the lessons from CAFS? CAFS developed this saga of 30 years. What was emphasized by CAFS experience was the difference between the culture of innovation and the culture of evolution. ICL and large food companies are very much in the culture of evolution, not innovation. Innovation can be used only in the sense of the evolutionary development of the existing product line. Do something that has a radical change or model development right across the company is resistant for reasons of not technical, more organizational than anything else. And I know, Hamish, I'm sure, I still have the evidence of the bruises on our head and banging our heads against brick walls. And I think we both became very aware during our selling exercise in ICL back in the mid-late 70s of the dictum of Thomas Edison that successful innovation is 10% inspiration and 90% perspiration. The success also is very dependent on individual enthusiasm and commitment by the various people who partake in the project. I've mentioned a few names this evening. Of course, there was a cast. I won't say thousands, but by the end, certainly some hundreds. But to get innovation through in a company into an evolutionary culture, by God, it helps to have friends at court, particularly if it's the king. So that was the decision made by Rob Wilmot. CAFS may never have come to be a broad spectrum product in the ICL product line. What about the future? I've alluded to some of these observations already. Culture of innovation is now much more widespread in the computer field. There are many new companies. Microsoft's capitalization firms are now the same size as IBM. And we see the extinction of the dinosaurs, or if not, if they don't become extinct, then we've got to undergo a sort of supercharged mutation and evolution. And anybody who's lived through ICL in the last 10 years knows what that means. ICL has changed its base, it survives, it actually makes a profit. But it doesn't, it's now a totally different company to what it was 10 or 12 years ago. say something like typical orders that it takes the hardware content will only be 20%. Not as it was in the past. The rest is value-added services. And that is a major difference for any of the companies. The industry is much more mature, stratify and buy components out, put them together, and sell the system. The workstation market, I already mentioned this, is also very much more receptive to the concept of accelerators. And we can certainly see CAFS-like devices going into workstations within the very near future. What about databases? The problem with databases, particularly large ones, are getting worse rather than better. The current data models they use are inadequate to represent the problems with which we wish to deal. We are faced therefore with two problems. One is actually raising the level of abstraction by which the databases are described. And having done that, that introduces problems of performance. We then have a problem of building engines that will actually make these things run in a manner which will support interactive working. And we certainly see that things like CAFS chipsets are really only the beginning. We'll probably see an increasing number, as we see in the graphics field, for special purpose architectures being used at the back ends of machines to handle many of the problems that already exist and will certainly appear in the future in this field. Ladies and gentlemen, thank you very much.
Thank you, Dick. Would you get Dick to do it?
If we get the house lights on, please.
The CAFS seems to be simply for handling data on rotating mass stores. I wasn't quite clear about the chipset. The chipset needs with it a rotating mass store.
Well, yes, George, the problem here is finding a single backing storage that works what technology that we've got. And at the moment we have, I suppose, all the large computing systems, 3 levels of storage. There's the random access, sending back memory, those programs are executed. There is some form of backing store, which usually is a disk of some kind. We may have tapes or optical disks as a third level of tertiary storage beyond that. Nobody has managed to produce an alternative technology to the rotating either magnetic or optical memory. The memories fall into 2 categories. There are those in which you have the location of information stored as essentially static in space. You access it by passing currents and electric wires. Random access memory works. And those where you have a single receiving and transmitting head, as it were, and you move something containing data underneath it. And although semiconductor memories are getting bigger, we can now build machines with several hundred megabytes of random access memory. But unfortunately, the problems that we're dealing with get bigger too. And all that happens is we improve the goalpost a bit. And so we may have 100 megabytes of RAM on our machine, or on a cluster of processors. We probably have 10 to 100 gigabytes of disk storage, getting all the information that's appropriate to it. So each stage, I mean, it's amazing now. When we first got the first CAFS engine, we had an 8 megabyte disk, all we had at that time. If you heard the Apple Mac I use at home, it's a 400 megabyte disk. And I'll never believe on personal applications could fill 400 megabytes. So I filled 250 of them, and I managed to fill that disk up very fast. It's amazing, nature abhors a vacuum, and things that expand the fill space available. It isn't all garbage. It's just that new opportunities are presented, and of course, new information is stored. So we see this thing as a continuous movement. So what we have got is an environment where we see the backing storage is essentially going to be magnetic or optical for the foreseeable future. There will be an alternative technology to appear. However, there are very large semiconductor memories available, and one can, of course, make semiconductors look like a RAM disk. And not obviously a CAFS-like device. It's a search engine, it can search both ways. And indeed, they were never actually used, as far as I'm aware, in the DAE architecture, the CAFS ISP channel could in fact face both ways. It could insert data coming off the disk, and also insert data coming out of the store. And the very reason, of course, why one can't conceive of this thing being built as a staging device, which one may have a cache memory, let's say, many tens of megabytes of RAM, very fast access, which one can access from CAFS as well as accessing disks. Such development is certainly possible. But I think one still has to face the fact that the backing storage for the foreseeable future is going to be magnetic optical. And spin, involves mechanics.
Yes, I was thinking of CAFS as something that took the pain out of having to do multiple access to rotating media, as you were saying, right?
Well,
it's a little more difficult to conceive it, but it's at a one level say a conductor store, however enormous, can one not calculate there?
If you've got the information to at the store, of course, again, the problem is how you access something in a general random access storage space. You can only do it by calculating where to go. So sort of information has to have some explicit referencing structure to get there. Otherwise, one just has to read every information serially and take out and examine the information itself. Now, it comes back to the same argument. If we do the Tracy argument in a random access array, the same arguments apply. A very complex referencing structure needs an awful lot of instructing the execute to find something. And if one goes into any sort of elaborate matching, which cannot be handled by some explicit referencing structure, one has to search. If one, I don't show you my two cases. The Brzezinski name is one, but if one wishes to make a comparison, let's say, of a record of data, and one wishes to make a selection on the basis of comparison of terms in the same record, particularly inequality of operators, an index can really doesn't help you very much. Or at least if you try to construct an index, there's so much effort in constructing it, it's actually simply going wrong.
I'm a little confused as to where the acceleration is really coming from. In the case of the original hectotrack disk, I can see it was coming from the parallelism of having scans from each of the heads going on at the same time. Further down the line, presumably, we're now no longer talking about hectotrack disks. It sounds awfully like simply having better processing that's very close to the head.
That's what it is. We never use hectotrack disks because their capacity is limited to the very simple application. All right, managing some sort of central directory files. But we always use the ARM file. What the original was to read from many heads simultaneously. So we had a multi-head read from something. But that was merely to jack up the data rate to something that was sensible, like 3 megabytes a second. We always foresaw disks having a transfer rate that would go up to 3, 5, 10 megabytes a second per channel. And what we did see happening was that as that disk speeds went up, the VLSI technology enabled us to build a repeatable module, a small chipset, which would go behind the head. So you're right, yes, it becomes a special purpose processor behind the head. Now all it's doing there is executing a certain set of functions very fast. It's a filter. The operations themselves cannot easily be done by a conventional processor at current disk states. One can build it if you do it, but it's a big, expensive machine. Like that's what you can do with specialized hardware. So one now sees the cigarette pack, as it were, of chips behind the recording head costing a fairly small sum of money, able to do the equivalent processing power, perhaps a 400-bit 32-bit machine. And you can't get more 32-bit machines for pence. You can get obviously 10, 20, 30-bit machines now. You stack that and cost next to nothing. But they're still order of magnitude away from what this hardware can do.
So this is something that's different from a digital signal processing, for example.
Well, there are similar analogs there because these again are special purpose chips that can handle, do effective processing at very high speed.
Just one more supplementary. Why isn't the bottleneck the access time moving the heads across the disk?
That is one of the big limitations of any mechanical storage device. There is mechanical inertia involved in moving something somewhere, yes. And of course, if one's searching a lot of data, one can obviously do clever things with placement, so one minimizes the actual overhead movement that one actually has. So it's just a little bit notch across and one still the next. Clearly, using a cache-like device, of course, does not mean you always search. I mentioned earlier on the idea of partition in the investigation. So quite clearly, we have this problem in storage medium, because it's essentially linear. Chopped up small fragments, but it's essentially linear. And we can be able to invest individual fragments, and then we search the full fragment. So clearly, with the CAFS system that we've got here, all do some form of indexing. But the indexing does not have to be at the resolution that's associated with conventional indexing schemes. It's much more a cellular approach in which you store information in a category in the cell which you search. We try and arrange placement and such, but the volume is quite small. The analog I like is this. If you're all concerning, let me ask you a narrow question. How do you organize your personal file list?
I make it self-descriptive.
Yes.
So, for example, the name of the file contains the topic and the date, and therefore it automatically orders itself.
So in time sequence?
Yes, in time sequence and clusters that. sorted within topic by type sequence automatically, because that's the collated set.
What you're doing is what most people have found in their personal filing system. First of all, one of the major dimensions of collation is time. And usually it's under some sort of core subject classification. And they don't try anything very, very detailed. There's no collapse or break down. Because very often, human beings are very good temporal and spatial map of data. It's like a desk system. Will be telling me to move stuff around my desk, I can't find it. So I know full well I know a spatial map which says it's over there, and it's at a certain time it means to sort of do stuff at the bottom of that pile. And I can then do a small search and find it. And I found that most people, if they're frank, will admit something of this kind. Now, what one can see in the CAFS system, of course, we can now do the same thing on a computer system. And when one starts to look at applications that way, storing data in time sequence, one can get much more efficient packing. The archiving problem is simple. You can roll off one end and come on the other. One doesn't have to tweet anything. All the information pertinent, let's say, processing order can stay there. Multiple copies can stay there. Each one is date and timestamp. The audit trail history is all there. It's all in time sequence. All quite dense and packed. Quite different way of handling applications from the way it's classically handled. And things like this can get over many of the problems associated with moving electromechanical machines nonetheless. We'd love to have instantaneous random access on disks. Unfortunately, the technology doesn't exist to do it. So with all the limitation, yes, and if you're moving heads around, that's a severe limitation. Indeed, one anecdote there which I like is that, yes, early 70s, 70 through 73 actually, between years ago, is when the Codicil database task group were deliberating on the DBTG data model. And the fellow from Bell Labs, if I remember right, was a chap called Wilma Taxidis. And he gave a seminar in London, which I went to, and he was talking about the rationale behind the approach they used. And he made a statement which I thought was absolutely wonderful. He said, of course, we decided to use the software principles of this processing because we now have a random access file store available moving on this file. And I thought, wait a minute. In theory, it's random access, yes. My mind was locked into heads jumping backwards and forwards. Hydraulic actuators sort of squelching away. In comparison to random access in a conventional call or sending up in memory. The difference in access time is several orders of magnitude. And I always find fascinating watching a sort of well-tuned DBTG database being well worked. It's a marvelous example of life testing instruction, the diskette actuating mechanism on disk drives. It's flashing back all over. Now, clearly, of course, the response is very slow if one has to move heads in following pointer chains. And of course, with the Codicil system, you map the records appropriately and store them together, very frequently used together and stored in pages. It worked very well, very fast. The moment you went down a different path, as lo and behold, of course, the linear mapping was no longer relevant. One had to sort of move around a random access address space. And of course, the head movements. There's no way around that problem unless one duplicates data, which of course the reason others want to do. The only, even if one has the sort of CAFS system, one still can't get away from the fact that one has to move. One only has a one-third dimensional mapping, and so it has to move around. What one can only do is to try and layer things out so we minimize it. One can't get away from that no matter what data model, what implementation method one uses. There still is the problem of fragmented data across address space, which has to be searched by moving machinery around. Yes, we'd love a 100 gigabyte random access memory. It's cheap.
How did CAFS compare with database systems that used indexes when the item of data that one was looking for was not actually there? Did that imply that the system had to really basically read every single byte on the disk from beginning to end?
Because of course indexes were used. If one had a, let's assume we had we use some sort of index sequential system, which is one of the ways we did it, which has a cellular structure, in which they was collate long-term primary key access. The index, the index simply said if this data existed, this was let's say the key that was given, it relied on a certain range, and therefore it existed on a certain cell. One may have to search that cell. If you were null when you wasn't there. One couldn't tell from the index it wasn't there. It's true. But on the other hand, if you only required one, very often because of the coarseness of the index, the whole index was made store resident.
Yeah.
So you've got one disk access and you found it out, which in most cases of an index sequential system would involve one to disk access anyhow, just supply the index to the null itself. So in fact, it's not the same. So the thing is that anytime access, like a conventional access, an index sequential access, can be just as efficient on the CAFS, probably perhaps even more so than it can be with a conventional system. Because the architect is able to subsume all the existing systems and use them with loss of efficiency. But it has the added facility, of course, that it can seamlessly move into an extended searching requirement.
Using your telephone directory as an instance, I can see how it can find the Acacia Avenue or Acacia House or whatever. But what if you wanted to actually print a telephone directory with people's names in alphabetical order? Now, was CAFS used for that type of work?
It wasn't a sorting engine.
Yes, it was really an interactive inquiry system rather than
what we did when we did those trials, we simply put the information created that wasn't a telephone book onto a disk file. And the access mechanism was in fact the primary key was used in the concatenation of the first few characters of name and initials. It wasn't like telephone book, in fact. And you had a cellular structure to go and search that cell. There were secondary indexes, and based on we haven't described it, we had inverted index system as well, which are also pointed to cells. It was a loose, much coarser structured index than a conventional one. And all we ever had to do is to tell us where the information was, and really, it wasn't tell us where it was, tell us where it might be. You had to go and look. So one of the duties of that type of structure was, and of course, if you amended any of the records, you didn't have to necessarily change the index themselves, other than to make quite sure they pointed to the cell where it was. So old data was left, and the only overview would be when we go into the cell, which would not be anything that was useful. Every so often, one would do a tidy up operation. So the index maintenance, the generation maintenance, is much simplified.
one could do a wild card, excuse me, that Polish or Hungarian name that you wrote down on the slide earlier, one would find that entry by saying a wild card and then typing in the last 3 characters of the name. Is that how it would? And then you were actually doing a sliding match.
I use this one because this is this particular one, too much even for the first CAFS machines. It would handle something like VR don't care SKI. It didn't do that one all right. It used to be a little elastic match in the middle. The double elastic match, that at least in principle will now be done by the new VLSI CAFS. I mean, that's a fairly extreme case. This one is really powerful enough in most situations. And those sort of things have proved extremely useful in types of text searching. Other things I can describe in this, also the hardware contains facilities for handling weighted core functions. So any M things. Now those sort of search operations are very difficult using indexes, not even possible. Whereas with the search engine approach, they're very efficient.
It's still a valid proposition to say that the speed up factor essentially comes from the proposition that if the store rotates anyway for reasons except that they then the access time, if you know where the thing you're looking for is a half a rev. The access time, if you don't know where it is still a half a rev. Yes. No other store has this property. So you can find something just as fast whether you know where it is or you don't.
That's true. Yes, I mean, there are certain refinements on this system which can be done insofar as if you had several requests on it, you could actually knew which sector it was in, you could switch the channel to that particular head, just that sector was coming round. So you could, so that gave you a certain speed up factor, rather than just sort of saying, well, someone on a track, we wait for the bot to come round. But it was those fairly modest gains, considerable increasing complexity.
But it's very obvious that not knowing where, being able to access something without knowing where it is obviously a good thing.
Yes. That's only true if you know which track it's on.
Yes, that's true. Yes, that's
Because I think in the case where you've got a specific address, saying this thing is in a certain sector or a certain block like this, It may not very helpful very much. It means because you still have to wait for it to go around.
Oh,
It does
yes.
mean there's a lot of traffic on this. You can say, oh well, I can go and do that one now, then switch channels and go and get that one next, rather than simply go to that particular track and wait on it now, wait for it to rotate. So a small improvement in throughput can be achieved in extreme situations. But in terms of the user waiting for an answer to that request, it makes no difference at all. The user, be it a human being on a terminal or process in the machine, still has to wait for this to go around regardless.
Another way of looking at rationalizing is it still valid? I'll ask you, is it valid? The most common thing which is done when you're accessing a store is to decide that you don't want it. It isn't what you want. And so the clever trick is to try to arrange that this very common operation for deciding you don't want it is done by the cheapest bit of equipment.
And that's the fun rationale behind it, of course, in the early days. That was one of the rationales in the early days.
Yes, that's right. Is that still true?
It's less so now because the problem then was when we first started, of course, serial file processing was still very much in use. And we looked with horror on what happened in many customer houses where they were going through files to amend, let's say, 1, 2, 3, 4% of records. The whole file was solemnly copied across the whole process. And then, obviously, with disk file, when people were moving on disks, then of course it's possible to have a transaction file that could just address those parts of the file, and that problem went away. But even then, what was interesting enough was a lot of scanning was done for report generation purposes. I remember it was the data processing manager of one of the big insurance companies around about 1978, CSC, which, and I actually asked him, I said, how much of time did your machine spend actually searching for data? And he said, it's a good question. I don't know, I'm going to find out. And he then examined his workload very carefully. The month he came back, he said, my God, 70% of our machine time is actually spent combing through files, various things, either for purposes of updating them, they're often quite simple, such as the old disk file, or they were just doing report generation, in particular report generation, which often meant scanning huge quantities of data. He was amazed, and indeed, when we looked back to the early 70s when we first started looking at the applications for CAFS, looking at the application side of CAFS and ICL. One of the very first questions I asked the marketing for ICL was, have you any application profiles which our customers have, how they use their machines? We know what they use the machines for, and they hadn't a clue. They knew how many machines were sold in what market, but they hadn't a clue what their customers used them for. And they said, if you find out, do tell us. So they recognized it was a valid question, but it actually, when we started talking to customers, it's actually quite difficult to get the information. But one very interesting bit of information did emerge very early on, and that was that we looked around the popularity of all the ICL packages in the field. We found a thing called Find2, which was nothing more than a file reporting program. And this thing had sold more copies than any other application program sold by ICL. And then we saw things like the NCC's file tab was similar sales here with them. So because the functionality of the program and what it was doing was not a million miles away from the functionality we were putting in the CAFS hardware. And the very first CAFS machines, indeed, could be argued that they were a hardware version of file tab or Find2.
Is it very copied yet?
Yes.
Yes.
There are one or two machines around which are somewhat similar. But it's very interesting what actually happened in that marketplace because two things happened. In 1971 and 72, at the same time we started, we went to meet other companies who did the same thing too. And two trends were made in the States. There was one school went down the path of text retrieval, scanning large volume of text. And the other part went down the path of building relational database engines. And we were quite happy to see them go down these paths, but we knew they were wrong. Because the clear thing was to find a data description system which would actually subsume both. And that was one thing we got right. So we weren't dependent upon that particular limited domain. In terms of relational databases, there were two companies that in certain states came to market with machines, Britain Lee and Teradata. Now, the problem both these companies had was they were selling back-end machines. And very early on, we looked at an ICL the idea of whether we build a freestanding engine or whether we actually incorporate the system as a function and supplement within the existing architecture. And what became absolutely apparent very early on was that we had to build this thing deeply. It had to be a deep component of the architectural system. So the operating system actually had full knowledge of this device. to use it efficiently. Now this was, of course, something that was denied any manufacturer on the OEM basis trying to sell it in the open market. Something could bolt on to an IBM machine or use that machine or anybody else's machine. So the CAFS was a special purpose function architecture that was designed under the control of the computer builder. Now none of the other computer builders at that time pursued this particular course of development. And indeed, I had a very interesting experience myself at a seminar in Monterey, I think it was about 1980, just shortly after we launched the CAFS Mark II as the CAFS 800. And I gave a presentation on what we could do, and one American looked at me and said, "This is on the market." I said, "Yes." "How much does it cost?" I said, $250,000 to come to the exchange. "It's too cheap." It should cost at least $500,000. And we've had numerous customers in the UK say, "Oh my God, we can't afford the £100,000 that it was in those days when it was sellable." Now, afterwards in the bar, I talked to this chap who was extremely familiar with the worldwide computer scene. He knew all about ICL. And he said, with a beard, "Why on earth did I start out with that He said, "There were similar companies, many American companies, they all got killed. You got that machine, they threw it. It caused too much aggro in terms of the organization of the company. They weren't set up building innovative things of this kind. And so those are innovations in the States always come from small companies. How has it been successful?" I said, "You really want to know?" He said, "Yes." I said, "Ah, well," he said, "we haven't got that tight, so-called tight American management yet, English companies. It's a much looser structure. People are loath to make decisions, chopping things off. They tolerate the blow of rock. And only in extreme desperation will they actually say, "Look, we've got to stop this." And I said, we were not discouraged. We've got particularly encouraged. We were tolerant. And it was only that the thing had grown to a scale where they could no longer be ignored. We got through. But at that stage, we still hadn't finished the product. We still hadn't got the commitment for them to go ahead with the right product. As far as other machines in the States were concerned, well, Teradata built a relational back-end machine, which is on the market. It sells quite well to the IBM environment. It's got other clever features. It's very good at handling relational joins. It's not much good at searching. The Britain Lee company went bust. There were one or two French companies that built simple search engines. As far as I know, one or two are still in existence. But they're all operating in rather small areas. And the problem they all faced was they weren't system builders themselves, and therefore they couldn't build the things into a component within the system itself. You could only build it as an add-on. And the add-on market was premature. Now what I believe that's what will happen now. We now do have an add-on market, particularly in the personnel and the workstation field, where the standards are all very open. And we can now talk about building accelerators and plugging them in. And there's a whole huge business of companies making go faster goodies, selling into that market. So quite different environment. And it may very well be that some database agents will actually now get in that market, and that could cause a sort of trade-off.
How many did you say had been sold?
I have no idea.
Oh, sorry.
It's a standard feature now. All ICL has been for 10 years. So every disk control you buy, you've got a CAFS, at least one CAFS. I think the average population is about 2 CAFS modules a second.
More than that.
I
would think it's certainly well over 10,000, possibly multiple tens of thousands.
I mean, what we always hoped for with building was that the CAFS unit actually not become not significantly in its own right. It would just become a natural feature of the different subsystems. And the challenge would have this.
In a way, that may have worked against you because it's embedded in the system. It doesn't strike people who are not ICO people. It is actually there. It is there, and it's a very important part, but it's actually part of the system. Therefore, it doesn't appear as the CAFS box or something like that, quite so clearly.
May I comment on that? The same applies also equally to ICL people.
Oh.
The latest figures I have, we've got about 23 major applications which are exploiting CAFS in the company. There are 4,000 registered users of those applications, and they're generating something like 16,000 to 20,000 inquiries a day. And they accept the response time because it's the natural way of doing it. They don't realise that there's a CAFS engine underneath.
I mean, one of the things being in high technology games, once you demonstrate something not working, using it. They take the technology completely for granted.
Yeah. The world has always been that.
On those ICL machines that have CAFS as a built-in, is the data, the CAFS data, separate from the other data that they may be using relational databases?
Okay, no, what's happened is we designed the CAFS ISP machine was designed to handle standard data formats. And also, but with the addition that you could also use the self-identifying structures as well. And that the self-identifying field format is incorporated into the data dictionary system by ICL, standard feature. So the whole thing can scan a conventional topol file, or in the case of the Unix machine, standard Unix files. So there's no requirement to withdraw. So the ingress files and relational files are standard relational files.
One extension of that, there are a number of database applications which are so heavily loaded with conventional transaction traffic and are optimized for that, that they can't support an inquiry load an ad hoc inquiry load on the same machine. There the answer obviously is to duplicate data and inquiry service separate from the parent transaction process. And if you're prepared to take that step, then you may choose to modify the storage sequence or the content to
Optimize it for the
optimize it for
particular
search.
application. Yeah.
What's actually happening is independent of CAFS, there's quite a number of operational environments there. Of course, the users actually they have production systems which are very heavily used online with lots of transaction traffic. We don't want this state unsuitable for direct management information, so-called. They actually construct other databases which are information with extraction production systems consolidated with this other database, which is essentially a read-only database, optimized for supplying answering more general inquiries, and of course it can be updated on a daily basis. And that, of course, is very, very compatible with the CAFS approach.
I think we'll stop there. Thank Vic very much for actually fascinating talk. Thank you very much.